want to make sure we have a documentation of this morning. Late start though it is. So anyway, yes, here we're going to finally be coming back to talk about continuous random variables here. So kind of your intuition was discrete was the outcomes that you could have were some finite list. You could list them out 0, 1, 2, 3, 4, whatever. Or was some countably finite, countably infinite thing. So all the natural numbers, for example. Continuous random variables, on the other hand, are going to take on values in an interval. So you can't list out what all the possibilities are. It could be any number within an interval. And just to remind you, some examples of finite intervals here anyway, we have our notation. We have parentheses to denote an open interval, which means the endpoints are not included. Square brackets, of course, remember that means a closed interval. So for this one, the endpoints A and B are included. Again, you could also have an infinite interval, 0 to infinity, 1 to infinity, kind of whatever. There's just some examples and remind you of what the notation here is. So then actually most of what you'll encounter in the real world is going to be a continuous random variable. This usually involves variables that, again, like I mentioned before, can be measured. So things like height, weight, temperature, any number of other variables that you might encounter in your various experiments. Probably going to be continuous random variables. And just to note that we would consider them continuous even though sort of measuring scale has certain limitations. So if you're measuring the pH of a compound, of course you can't. I mean, your measuring tool only goes out to so many decimal points, probably not that many. So even though a measuring device, even though that doesn't read technically any number in there, we're going to treat that as a continuous random variable. So bear with me on that distinction, I guess. So again, continuous random variables often correspond to things that are measured. And so we can talk about the exact same things that we talked about. So things here in this chapter should feel familiar anyway as we make the transition from discrete random variables to continuous. There we talked about probability mass function, PMFs and CDFs. Here we're going to introduce some new terminology, but again the same idea. So when we have a continuous random variable, the probability distribution that we'll talk about for this we're going to call the probability density function, or the PDF. So it's not an Adobe PDF. It's a probability density function, and it sort of has the same sort of, the way you can think about it anyway, is sort of the same as the probability mass function in that it helps us calculate probabilities, and so the exact interpretation is different, and the way in which we calculate probabilities is different, but it's the same idea. So the definition here is that any function, little f of x, such that for any numbers a and b with a less than b, the probability that x is between those numbers is now that integral on the right side of the screen. So whereas in chapter 3 we were doing summations, here in chapter 4 with continuous random variables we're going to be doing integration. So this is the formal definition here, and kind of to motivate us, there's this little picture in your notes, and thinking about, again, we've all had calculus in here. We kind of know what the interpretation of the integral is. The integral calculates the area under the curve between those 2 points, between A and B. And so this introduces this idea of this correspondence between probability and area. So the probability that x falls between A and B is equal to the area under the curve, under its probability density function between those two values. So this correspondence between area and probability is going to be what we'll use a lot in this chapter. And then we're going to also, so f of x is the probability density function. You might also hear me call that just a density curve. So that's the terminology that we'll be using in this chapter. Okay, so just like we had certain conditions that we needed to be satisfied for a probability mass function, there are certain conditions that we need to be satisfied for a probability density function. Again, there are two two conditions here. The first one, again, is that the density curve must be above 0 always. So we need f of x to be greater than or equal to 0 for all x. And that just kind of, again, gets to that idea that you can't have a negative probability. Your probability has to be positive. So the density curve has to be larger than or equal to 0 for all x. And then the integral from negative infinity to positive infinity. So there I'm kind of thinking about the total area under the density curve. The range of the thing might actually not be from negative infinity to positive infinity, but over the whole range, this thing is equal to 1. So think about the total probability, kind of like we saw before. If you add up all the options, give you a probability of 1 for everything. Same idea here. So the thing has to be positive, and total probability has to be 1. But just a kind of a quick warning, or something to note anyway, is that for our probability mass functions, the first condition was slightly different in that all the probabilities had to be between 0 and 1. For a probability density function, your PDF actually does not have to be. There could be values of that function f of x that are bigger than 1. So slight difference here as we talk about probability density functions. Questions or comments so far? Just kind of see where we're going here. We're making the jump from discrete to continuous. Okay. So here's a bit of a paradox, I think. So another way that back in chapter 3, when we were talking about continuous random variables, I said that they had to be defined on an interval. So that's something we already talked about. And then also that the probability that x is equal to any particular value is actually 0. So for any fixed value c, so for any real number in there, the probability that the random variable is actually equal to that value is 0. So why? So I'll show you. Well, so why is that the case? I guess it's a paradox because certainly x could equal 0, right? You could do the experiment and you could take a measurement and have it be equal to that value, but the probability of that happening is 0, which is kind of a weird thing to think about. So the mathematical reason here anyway is probability that x equals c. You could rewrite that as that's the probability that x is greater than or equal to c, and also less than or equal to c. That's the same statement there. And so thinking back, using that second probability statement and going back to the definition of a probability density function just on the previous page, this is equal to an integral of f of x, and the endpoints go from c to c. And so that thing's going to be equal to 0. Maybe it's more helpful to think about this thing visually. Again, I jumping back a few slides, made this kind of highlighted that probability corresponds to area. So if I pick a point C right there, again the area, if I'm only considering that value, sort of the area under the curve is just that line. So there's no, and a line of course has no area. So if you were to calculate the area of that line just being exactly right at C, that thing has area 0. So I don't know. I think it's a strange thing, but it is true that certainly C is a value that I could get. I could be taking a pH measurement and I wanted to see the probability that it equals 7. It's a value that I could get, but it has probability 0. So again, that's a weird thing, but for continuous random variables, that is true. Do you guys believe me? Do you questions, comments? Yeah.
And another thing, when the PDF is greater than 1, what does that mean?
When the PDF is greater than 1, what does that mean? Great question. That simply means that the value of the PDF at that value is bigger than 1. I mean, so you can't.
Does that mean it always will occur?
Does that mean it will always will occur? No. So for probability mass functions, we talked about the probability that x was equal to some value, and that had positive probability. It's like, what's the probability that I roll a 2 if I roll the dice or something like that. Again, kind of what I've just shown you here. This is true for any value. So if regardless of what the functional value of the probability density function is, it doesn't tell me the probability of that event happening. It's like you have to think about probability as you would think, instead of thinking about the probability of getting exactly a 7, you could talk about what's the probability I get 6.5 to 7.05 or something. So you kind of think about a slightly bigger range to answer those kind of questions. So we won't use, the PDF will not be used in the same way as the probability mass function was used to talk about probabilities for specific outcomes. You'll more look at a range of values to talk about a probability. So if the probability density function is bigger than 1, it doesn't really mean anything. It just means that the functional value of the probability density function is bigger than 1. Yeah. So that doesn't really give any interpretation about the probability. That's a good question. Any other questions you guys can think of? Why are we dwelling on this? Okay. So anyway, that's just a little fact that we can talk about. Okay, so that's the probability density function is sort of the equivalent of the probability mass function. For the cumulative distribution function, we're going to call that the same thing here. So for discrete and continuous, we'll call that the CDF, and this part is exactly the same, right? The CDF is still the probability of being less than or equal to that small value lowercase x, but we'll now calculate it in terms of an integral instead of a summation. So the probability of being less than or equal to x is just you integrate the function over all values less than or equal to x. So same idea. Before we were summing up all the probabilities of being less than lowercase x, and now we're integrating over all values less than that. So the interpretation is exactly the same of the CDF. We just calculate it using an integral instead of a summation. And you can kind of think about so the CDF will have similar properties, is that it kind of but now instead of being that step function like we saw in chapter 3, instead of kind of jumping up at particular values and being flat, it's now going to be a smooth curve. So that the area there will increase continuously as your endpoint gets bigger. So because the PDF f of x is a smooth function, your CDF will also be a smooth function. Okay, so properties of the CDF for a continuous random variable. Many of these are the same. The first 3 points are exactly the same as what we saw before. The limit as you go off to negative infinity is 0. The limit as you go off to positive infinity is 1, and it's non-decreasing, so it's always going to be getting bigger. But now, because we have a continuous random variable again, the CDF is also going to be continuous. And again, intuitively, you can see that from the picture on the previous page. But we can kind of generalize this just a little bit. If I want to find the probability that x is bigger than some value, strictly bigger than some value, again, now I can take 1 minus the CDF. And again, that's we didn't write it out like that, but that's something that we could have written down for the discrete case as well. So again, if here's my density curve, and I want to know the probability of being of being larger than being a, of being larger than a, I can just subtract off. I can take 1 minus all the other area there. So it's kind of the same. Kind of that complement rule here in terms of a random variable. And then finally here, the probability of being less than or equal to some value is the same as the probability of being less than that value. And why is that the case? Well, again, you can write out the probability of x being less than or equal to a is the probability that x is less than a plus the probability that x equals a. So I can just split that into two cases there. And again, as we saw previously, the probability being exactly equal to some value is equal to 0. So this is just the probability that x is less than a. So again, when you can be a little less careful about the endpoints here because the endpoints don't change the probability. Okay, one more fact here about CDFs is just kind of to remind you again of this of how we can calculate a probability like we're interested in doing there. And I'll say another note about this in just a second here. But if I want to know the probability of being between some values, I can use the CDF to find that probability. So again, as the picture highlights, this thing is the probability of x less than or equal to b, and this thing is the probability of x less than or equal to a. And so if I want that interval, I can just subtract those values. Questions, comments? Is this making sense? Am I going too fast, too slow? Okay. So before we move on, I just wanted to kind of put this summary up here to again kind of remind you. This is not in your notes. Just remind you the comparison here between these two things. So for a discrete random variable, again we have our probability mass function, and our CDF. So CDF again is the same in both cases. So discrete probability mass function, continuous, we have a probability density function. To find probabilities, then we can it's a similar idea, but in the discrete case, we're going to be adding up individual probabilities. So if we want the probability being between A and B, we can add up those values of the probability mass function. Whereas in the continuous case, we're going to be doing integration. So we'll do some examples of this, but just kind of in general, this is the separation between these two things. Discrete case, we add things up. Continuous case, we do integrals. Okay. So let's see. Let's quiz your calculus knowledge here. So proposition for you here. So if we have a continuous random variable and its PDF is lowercase f and CDF is capital F, then we can make this statement that at every point x which the derivative of that CDF exists, that derivative is going to be equal to the PDF, that same value. It's kind of a nice property here. So, and again, this is this is an application of the old fundamental theorem of calculus. The fundamental theorem of calculus. And I won't ask you to tell me what that is. We'll just talk about it here. So again, f prime of x is the derivative of x. So the derivative with respect to x of f of x, capital F of x. So again, we can write down what capital F of x is. This is the integral from negative infinity up to x of our density function. So again, I'm just writing things down, everything by definition so far. And then the fundamental theorem of calculus lets us say that that's equal to the PDF evaluated at x. So when you're taking an integral over some function from negative infinity up to x, and then the derivative of that, again, it's kind of like you're just doing, you're integrating and then taking the derivative, and you get back the original function. So this again kind of highlights the connection between, back in chapter 3 we saw, if I tell you the probability mass function, you can tell me the CDF and vice versa. Same idea here. You tell me what the probability density function is, I can tell you what the CDF is, and vice versa. So, and this is the connection here through taking derivatives. Okay, so let's stop talking about facts and proofs, and let's do an example here. So for some generic random variable x, which represents measurement error, I can write the CDF as follows. So x is less than -2, it's 0. If it's between -2 and 2, it has functional form, and bigger than 2, it is equal to 1. And so we want to use this now to find out some things about the probability density function. So that's my CDF. How do I get back the PDF? So again, this is going to be the derivative So the PDF is going to be the derivative of the CDF. So f of x is equal to the derivative with respect to x of what the CDF is. So I have a half plus 3/32, 4x minus x cubed over 3. And I guess I should say for x between, well, so if x is between -2 and +2, this is what the PDF will be. Okay, and so practice here. Derivatives here, derivative of a constant goes away, so we have derivative with respect to x. This is equal to 3/32. And I can pull the constant out, 3/32. What's the derivative of x? So the derivative of just of 4x is just going to be 4, right? So derivative of x is just 1. So it's times 4. Excuse me. And what's the derivative of x cubed? 3x squared. There we go. So we have 3x squared over 3. So we get some things to cancel. And this is 3/32 times 4 minus x squared. Again, 4x between -2 and +2. Okay, and so outside, you can kind of just think about outside of -2 and +2, the PDF is going to be equal to 0. So f of x equals 0 if x is less than -2 or x is bigger than 2. So inside that window, I have this functional form here. Outside of that, outside of that -2 to +2, I have 0 for my PDF, just 0. Okay, so we can now use we can use either one of these things to calculate a probability of interest. So let's think about how we can use both of them. So let's start out with the let's start out with the CDF. So if I want to know the probability of x being bigger than 0, again, according to fact number 5 on page 2 of your chapter 4 notes, this is 1 minus probability that x is less than or equal to 0. Which is 1 minus the CDF evaluated at 0. And if you look back to your CDF, this is just 1 minus 1/2 plus 3/32 times 4 times 0 minus 0 cubed over 3. Just plugging in 0 into my CDF, and that's going to be 1 minus 1/2 or 1/2. So again, I'm just plugging 0 into the CDF there. It's kind of the maybe slightly more direct way of finding this. Okay, but again, I can also use the PDF to figure out what this thing is. So again, the probability that x is bigger than 0, I can just take an integral from 0 up to infinity of my PDF. So on all values bigger than 0, you can simplify this slightly because when x is bigger than 2, the PDF is 0. So this is the same as going from 0 up to 2 of f of x dx. Next, I'm going to go ahead and fill in what that PDF is here. This is, we found this to be 3/32 times 4 minus x squared dx. So this is kind of going backwards now from what we already did. This is going to be 3/32 times 4x minus x cubed over 3. Again, we need to evaluate that at our endpoints, 0 and 2. And then if you plug those numbers in, you will indeed get 1/2. So gloss over that step for now. Well, maybe I'll just write it out really quickly. So to evaluate that, it's 3/32. First, you plug in the larger endpoint, right? So 4 times 2 minus 2 cubed over 3. And then subtract off plugging in the lower endpoint. And that, if you calculate that out, should give you 1/2. Okay. Why did I use 2? Yeah, good question. So why did I go from here over to here? Yeah. Yeah. So that was due to this fact up here. So the PDF when I get bigger than 2 is just equal to 0. So the function will just be 0 from 2 up to infinity. So those are going to be equal. Yeah. Good question. Yeah.
There's no constants for these integrations.
So when we have are there constants for the integrations? They cancel out, right? So when you have a definite integral here where you have the endpoints, you don't have to worry about that. Yeah. Good question too. So yeah, so I don't know if you had a calculus teacher who marked off huge points if you did an indefinite integral and didn't put like a plus c on the end of that. I did. when it's a definite integral, you don't have to worry about that. Okay, moving on. So that's what the PDF and the CDF are. Just like for the discrete case, we can again talk about expected values and sort of the intuition and everything else. The interpretations is exactly the same. Again, now we're going to be integrating instead of doing sums. So the expected value of x, before it was summation of x times the PMF. Now it's x times the PDF. And again, that gives us sort of the expected value, sort of a typical value you could expect, or think about the balancing point of the density function, of the density curve. And similarly, if you have a function of x, it's sort of the same, exactly what you would expect it to be based on what we saw in Chapter 3. So just take that function h of x and weight my density curve according to that and integrate over the whole real line. Again, I hope, is this starting to kind of feel familiar? Like, is this what you would have expected to see here? Kind of building off what we saw in Chapter 3. So then, can anyone guess what the variance is going to be without looking in your notes? So we can talk about the variance just like we can talk about the mean for a continuous random variable. So again, this part of the definition is exactly the same as we saw before. The variance of our continuous random variable is just the expected value of x minus its mean squared. So that part's exactly the same, but now to actually calculate that, we do an integral instead of a sum. And the nice thing is that our little shortcut calculation still holds up here. So it's still, that will often be easier again than calculating the thing on the first line. And then the standard deviation is just the square root of that. And all of the properties of expected values and variances that we discussed back in Chapter 3. So expected value of a linear combination of x, again, we knew exactly what to do with that. Variance of a linear combination of x was, there were rules and formulas for that as well. So all that stuff holds here as well. And I won't bother writing all that up again. Are there any questions you guys can think of on sort of this new material here? Yes, sir.
It's not really on this material, but like, so how do you get from like you have x minus mu squared to like the bottom equation? How do you actually get between those two?
Good question. How do I get from this line to the step down? Yeah, let me write that out over here. So expected value of x minus mu squared. Well, again, remember mu is the expected value of x. So I'll put that in here. So if I actually write out what that is if I expand that quadratic term, that's going to be the expected value of x squared minus 2x times mu plus mu squared. So I'm just expanding that quadratic term. And again, so the expectation I can take it's a linear operator, so I can separate those things out into three separate things there. So this is equal to expected value of x squared minus the expected value of 2x times mu plus the expected value of mu squared. So mu is a constant, right? It's just a number. This is like when we had the expected value of a times x, we could pull the a outside of the expectation. So this is expected value of x squared minus 2 mu times the expected value of x plus mu squared. And again, now I'm going to take advantage of the fact that mu is equal to the expected value of x. You see where this is going. Sorry, let me come up here. This is equal to the expected value of x squared minus 2. So again, mu is the expected value of x, so expected value of x times the expected value of x, and then plus mu squared is just quantity expected value of x squared. And that gives us the thing that was listed there. So this is expected value of x squared minus the quantity expected value of x squared. Is that okay? Did you follow that? Yeah.
What do you know expected value of mu squared equals to mu squared?
So how do we know the expected value of mu squared is equal to just mu squared? Mu squared is a constant, right? It's just it's a number. It's 2 or it's 3 or it's whatever. So one of those properties we saw, the expected value of a constant is just that constant. Yeah. So that's a good refresher of those general properties. All right. Any other questions, comments you guys can think of on what we've talked about so far? Okay. Let's do another example and apply some of these things that we've talked about. So here, let's look at the current in a certain circuit measured by an ammeter is continuous with the following PDF. So f of x is equal to some linear function there. If x is between 3 and 5, and 0 otherwise. So let's graph the PDF and then double check to make sure that it is a PDF, that its density curve, the area under its density curve, is equal to 1. So here I did my homework ahead of time. So between 3 and 5, this is x. This is the density curve f of x. When x is equal to 3, the density is over here at 0.425. And when x is equal to 5, jump up here to 0.575. And the density curve is a straight line in between there. You can pretend that's a straight line. And it's 0 otherwise. So I'm just graphing this one chunk of the linear function between x equals 3 and x equals 5. Okay, and then let's so that's our picture that we can think of going forward here. But to double check that this is actually a PDF, that the area under the curve is 1, let's do a double check there. So we want to see if the integral from negative infinity to positive infinity is equal to 1. Again, so the PDF is 0 outside of 3 to 5, so we can just shorten our endpoints there. This is from 3 to 5 of our density function, which is 0.075 x plus 0.2, all that, times dx. And of course we all know how to take integrals of polynomials, so this is just 0.075 x squared over 2 plus 0.2x, and I want to evaluate that thing at 3 and 5. So this is 0.075 over 2 times 5 squared. Then I'll subtract 0.075 times 3 squared over 2 minus 0.2 times 3. And double check that does indeed give you a 1 there. Everybody with me so far? Okay. So again, let's practice going from the PDF to the CDF. So again, for x between 3 and 5, the CDF, capital F of x, again, is the probability that our random variable x is less than or equal to some number lowercase x. And again, by definition, that's just negative infinity up to x of my density function. And again, because my density function only has positive probability for x bigger than 3, I can rewrite this as the integral from 3 up to x of 0.075 plus 0.2. Oh, I'm sorry, you guys. You guys need to call me out on this. It's bad notation. Sorry about that. So why does that bother me? Anybody? No idea? It's very bad practice to use the dummy variable as one of your limits of integration. Being picky there. Okay. Anyway, so we already calculated this antiderivative. Let's write it out again. So this is just 0.075 over 2 times xy squared plus 0.2y, again evaluated at 3 and x. And I'm going to let you actually write that out if you want. What you should get is 0.0375 x squared plus 0.2x minus 0.9375. And so, of course, the CDF, we want that to be defined for every value of x. So let's rewrite that here. The CDF is equal to what we just found. So 0.0375 x squared plus 0.2x minus 0.9375 if x is between 3 and 5 and 0 otherwise. So for x less than 3 or bigger than 5, the CDF, I'm sorry, scratch that last thing from your memory. It's 0 if x is less than 3 and 1 if x is bigger than 5. Sorry about that. It's a Friday morning. So again, between those values, between 3 and 5, we use the integral to find what the CDF is, and for x bigger than 5, the probability of being less than that is 1. For x less than 3, the probability of being less than that is 0. Okay, so we can use this now to calculate probabilities again. Probability that x is less than or equal to 4 is just the CDF evaluated at 4. Which is 0.0375 times 4 squared plus 0.2 times 4 minus 0.9375 is equal to 0.4625. So the probability of being less than 4 is a little less than half. And again, remember from our picture, we've drawn out this density curve. So if there's 4, what I'm telling you is that this area right here is equal to 0.4625. So that's your visual interpretation of what that number is. Okay. we can use the CDF in that way. Let's now quickly finish up this example talking about the expected current, and then let's also find the variance of that current. So again, the expected value of x. Again, this is the integral over 3 to 5 of x times f of x. So just adding an extra x in there. Integral from 3 to 5 of 0.075 x squared plus 0.2 x dx. And that's almost what we calculated before, so this should now be 0.075 x cubed over 3 plus 0.2 x squared over 2, evaluated at 3 and 5. And that should give you 4.05. So, sorry, moving a little more quickly here. So again, that's my sort of expected current. That's sort of like the average current that I would get from this experiment. And again, here in the continuous random variables, I think it makes a little more sense to think about this as like a balancing point for the density curve. So if we again flip back to our picture, if you move over slightly to 4.05. If you can imagine that trapezoid as a solid shape, it would balance right at the 4.05 point. So that's kind of where the shape would balance if it was a solid shape. I was kind of thinking about where the density curve is centered there. Okay, so that's my expected current. And let's finish up talking about the variance of this current. So again, we're going to use this fact that the variance of x, again, is equal to the expected value of x squared minus the expected value of x squared. So we already calculated the expected current, so let's just calculate the other piece of that, and then we can use that to calculate the variance. So the expected value of x squared, again, the expected value of a function, I just do that same function to and multiply that by the PDF and take the integral over the entire support there. So that's from 3 to 5 of x squared times f of x dx. So this is from 3 to 5 of 0.075 x cubed plus 0.2 x squared dx. And again, 0.075 x to the 4th over 3 plus 0.2 x cubed over 3, evaluated at 3 and 5. Sorry. Going too fast here. This should be a 4. Again, if you calculate that out, that should give you 16.733. And that means that my variance of x, the variance of the current, is equal to 16.733 minus 4.05 squared, which is very small, 0.3308. Okay, sorry, went through the end of that a little quickly. Is that okay with everybody? All right. Out of time. It's Friday, guys. Thanks for being here. Enjoy your weekend. We'll see you on Monday. Thank you.
Also, was it your